Hey guys, video 3. I am back. I hope everyone's doing all right and been keeping up, and I hope it's been making sense. I haven't been getting a lot of questions, so either it makes sense or you guys aren't watching, and I'm going to assume the first. So if it's not making sense, please don't hesitate to reach out. I will gladly explain more detail. I'm trying to keep it very straightforward as much as I can and not get too crazy. So hopefully that's why it's making sense, and I hope it's going all right with you guys. Okay, so on that note, we are now up to page 10. We're talking about a new quantity called impulse. So essentially, we were talking about momentum, and essentially, if something has momentum, it is moving. It has mass with velocity. In order to change that momentum, you need to apply a force over a period of time. So the faster the object's going, or the more mass it has, the more momentum it has, which means the larger the force or the longer the time in order to bring it to rest. So essentially what we have is this quantity of force times time, and that's going to equal change in momentum. So if we recall, on page 1, we learned that force is change in momentum over change in time. If I rearrange this, I can say that change in momentum is therefore force times time. So applying a force over a period of time causes an object to change its momentum. This we are going to call impulse. Impulse of the external forces acting on a system is equal to the change in momentum of the system. So force times time is going to equal impulse, or change in momentum is going to equal impulse. Both of them equal each other, so both of them equal impulse. We are going to use the letter J for impulse. So J is impulse. So what we can say is J equals two things. J equals force times time, or J equals delta P. Remember what momentum is, mass times velocity. So this is mass times delta V. A lot of times I'll write it like that. J equals mass times change in velocity, which is your final velocity minus your initial velocity. If we were in calculus, we would talk about the integral of f of t dt, but we're not going to worry about that, so don't stress about that. And then if you wanted to plot it, what we have right down here is a force versus time graph. So the area under the graph is going to equal the object's change in momentum, because in order to find the area, you take the force and multiply it by your time, and force times time is delta P, change in momentum. So if you were ever given a graph, I would give you a graph that's, easy to calculate the area of. This one would be ugly. You don't really know the values there, but it would be like a square or a triangle, and you could just calculate the area under the curve to get the change in momentum. All right, so next page, again, I'm trying to keep this as simple as I can for you guys. Impulse and collisions. If you think of a collision, what the graph of that force looks like is this spike right here. Essentially, the force is going to start small, it's going to spike, and then it's going to come right off. This is what the graph would look like in real life. But that's uglier, that's harder to calculate, that gets a little crazy. So what we're going to talk about in this class is just the average force. So what is the force that is the average of that whole spike? So essentially, the area of this blue is going to equal the area of the purple. So there's the same change in momentum in these two, but instead of saying, okay, we get all the way up to whatever this max force is, we're not going to worry about that. We're just going to say, let's talk about the average force. So F average is the constant force, which gives the same impulse J in the same interval delta T. We're just going to go with average forces. Whatever the force is the whole way, what's the average of it? All right, so here's an example problem. We have a 140-gram baseball in horizontal flight with a speed of 39 meters per second. It is going to be struck by a batter. After leaving the ball will travel in the opposite direction with a speed also 39 meters per second. So let's draw a picture here. We've got baseball. I feel like baseball should be red. I don't know why. So we've got baseball. Here's my baseball. It is going initially with 39 meters per second. Then it is struck by the bat and is going to leave the bat in the opposite direction, also with 39 meters per second. So we want to figure out a couple things. Part A, what is the impulse? Well, impulse, we learned, was equal to two things: force times time, or change in momentum. So in this particular situation, I don't know anything about the force or the time. All right, so then let's use the other definition, change in momentum. So that would be final momentum, final MV, minus initial MV. Okay, the mass they tell us is 140 grams, which is 0.14 kilograms. The final velocity, be careful of signs. This is a vector. So my final velocity is in my positive direction, 39, minus my initial momentum, so 0.14 times the initial velocity, and that's in the negative direction. So the minus becomes positive. You can type all of that in. You get 10.92 kilogram meters per second. We haven't talked about the units of impulse. I'm just realizing that. The units of impulse are the same units as momentum. If impulse is equal to change in momentum, that should make sense. So you can either use kilogram meters per second or Newton seconds. Remember, those are your two options for momentum. Again, if you think of impulse, force times time would be newtons times seconds. Or mass times velocity would be kilogram meters per second. So both ways you end up with the units for impulse, they're equal. All right, let's go back to red. That's yellow. There we go. Part B says, all right, if the impact time for the collision is 1.2 ms. What is 1.2 ms? 1.2, that's milliseconds. So times 10 to the minus third seconds. We want to figure out what is the force. Well, luckily, we know that impulse is force times time. I just found the impulse. I know that it's 10.92. We're looking for the force, and I know the time is 1.2 times 10 to the negative third seconds. So when I calculate all of that out, I get that my force is 9,100 newtons. Yay! So there's my answer to part A. And my answer to part B is right here. All right, so hopefully that makes some sense. If it doesn't, let me know. All right, last page. Let's do one more. Here, we're going to talk if we have multiple collisions at once. So not just one, but numerous in a row. So we're going to talk about here, we have a paintball gun is going to fire R paintballs per second. Each has a mass m and speed v. We're just going to keep them m and v. In a real problem, you would have actual numbers and you can plug them in, but for now, we're not going to worry about it. They are going to strike a fixed target where they stop, and we want to know what is the average force exerted over a period of time that is long compared to the time between them. So essentially, I'm trying to find the average force. These are going to keep hitting this target, and there's going to be all of these spikes that are occurring, and I want to figure out what the average force is. So again, we're going to keep it just in terms of variables. If you actually had numbers, you would plug them in. But let's say we know that force times time is equal to change in momentum, which is mass times change in velocity. All right. That we can then say force times time equals mass times final velocity minus initial velocity. Well, the final velocity, they come to rest, so this really just goes to 0. So what we can say is that the force is therefore negative m. Initial velocity, they tell you, is just v over the time. Now, they don't tell you the time. They tell you the rate. They tell you it's r times per second. It says r per second. So r times per 1 second. If I want the time, then that means that we know it goes 1 over r seconds per time. So essentially, if it's 4 per second, it's a quarter seconds for 1. Does that make sense? Hopefully. If it's 2 per second, it's half a second per 1. So t is equal to 1 over r. So if I plug that in, I can say that the force is therefore mv over 1 over r. And then 1 over 1 over, I can flip that and say that's then just mvr. So again, this is very abstract right now because you don't actually have numbers. But if you had numbers, you could figure out the force required or the average force exerted on the target by taking the mass of the object times the initial speed it's going times the rate. And that'll give you the force. So you'll have some problems later where you can use that to actually calculate them. Awesome. All right, so problems are next. You guys will be working on those coming up tomorrow. I'll probably give you 2 days for the next 2 days. And yeah, life is good. If you guys have any questions, please, please, please do not hesitate to reach out. Awesome. Enjoy the rest of your day. Bye.